All right. Okay, now let's continue with our discussion of this, the solution of maintenance problem using this new algorithm, policy improvement algorithm. Right? What did we do? We arbitrarily picked one policy, right? In this case, the policy that we picked does not do anything in the first three states and replaces the machine whenever it fails, right? And the first iteration starts with step one, where we try to determine the value of this policy. We will try to find, right? We will try to find the long-run average cost per time unit. That's the performance measure we are interested in to minimize, right? And the other, we will, in the meantime, also find the relative values that which are going to be again useful or important in finding another policy that will be at least as good as the one that we started, namely R1. Right? Now, in the value determination step, the equation that we have to solve to find the relevant variables, right, are for each state, right, can be written like this one. So GR1, right, the long-run expected average cost per time unit for policy R1 equals, what am I using? I have this, maybe I should just switch it once, right? So we will just write these equations for each state, and I have four states, right? For state 0, what do I have? I need to remember the probabilities, right? One-step transition probabilities. Let me just put here at least the state transition, right? State transition diagram. That is going to be useful to figure out the expansion of these equations here. I have four states. Right? From state 0, you may remember we can go to state 1, 2, or 3 with probabilities 7, 8, 1/16, and 1/16. From state 1, you may come back to state 1 or go to state 2 or state 3. You may come back to state 1 with probability 3/4. Okay, so you can go from 1 to 2 in one step with probability 1/8, and with the same 1/8 probability, you may also go from 1 to 3. Right? From 2, you may either come back, or you may go to state 3 with equal probabilities, namely 1/2. Right? And then what else? Every time you are in state 3 with probability 1, you replace the machine. Therefore, the transition, one-step transition probability from 3 to 0 equals 1. Okay, and now we can use these to write these equations, right? So G of Ri, for state 0, the immediate cost equals 0, right? State 0 R1 equals 0, so I don't have anything. Then I have a sum of product of one-step transition probabilities with the initial values, right? Initial value or initial values of states, right? They look like what? From 0, you can first go to state 1 with probability 7/8. Then you will multiply this with V1 of R1, or you can go to state 2 with probability 1/16, and you multiply with relative value of state 2 under policy R1, and then you can go to state 3, but the relative value for the last state by convention is always 0, right? So we can write it here if you wish. So that term disappears. Minus, right? We used to add the relative value of state 0 to the left, but with the minus sign, we decided to take it to the right. So we have relative value of state 0 under policy R1. So that's the first equation that we have in value determination step. For state 1, we have the same long-run expected average cost, because we assume, but we know, in fact, when you look at this thing, is a Markov chain which is irreducible and periodic. Therefore, the long-run expected average cost doesn't depend on the initial state. Therefore, we have the same GR1s for all these states. On the right-hand side, we state with immediate expected cost we incur in state 1. If we apply policy R1, namely this, right? Now you start with 1. It was 0 before, right? It was 0. Now it is 1. And now from state 1, in one step, you can either come back to itself or move to state 2, or you can go to state 3, right? For each one of them, probabilities are like what? 3/4 time V1 of R1, 1/8 times V2 of R1, and plus, well, we don't count, right? So the relative value for state 3 was 0, so that doesn't appear, minus the relative value of state 1 under policy R1. Okay? We have now another equation for state 2, log run expected average cost under policy R1 equals immediate expected cost incurred in state 2, which is 3, plus from state 2, in one step you can either come back or you can go to state 3, right? With probability 1/2 you can come back, so you have 1/2 times relative value of state 2 plus relative value of state 3 is again 0, that disappears, and then you have to subtract the relative value of state 2 under the same policy R1. Okay? And finally, we have another equation for state 3, long run expected average cost of policy R1 equals immediate expected cost incurred in state 6, because you replace and then you lose production, it is 6. And from state 3, there is only one way to leave that state. With probability 1, you go to state 0. Therefore, this is 1 times relative value of state 0 minus relative value of state 3, which is 0. Right? So all three equations, how many unknowns? Just to check one more time. V0, V1, V2, 3, plus this G of R1, 4. I have 4 equations, 4 unknowns we can solve. Together with this, then we will have known all the relative values. Right? Then the simultaneous solution of these 4 equations, or 5 if you count this one as well, becomes, okay, the long run expected average cost per time unit for this chain becomes $1,923 in this case, right? The monetary unit was dollars for this question. And the relative value of state 0 under policy R1 is minus 4,077. And relative value of state 1 under policy R1 becomes minus 2,615. Relative value of state 2 under policy R1 becomes 2,154. And just to put everything together, we know that the relative value of last state equals 0. Alright? So we are done with step 1. Right? In step 2, we are not trying to find a policy which is at least as good as the policy that we just studied. Right? So therefore this is called policy improvement step. Okay. And what do we do here? We now define or come up or construct a new policy. Let's call it R2. And this is going to be the policy, okay, which assigns, let's say, to state I, an action K, right, which minimizes the so-called policy improvement quantity, right, which minimizes, okay, the following policy improvement quantity. Okay, they are going to be different for each state and for each k, of course. Right? Let us write them for each state. For state 0, what do you have? Now, this is the immediate cost, expected cost, incurred in state 0 when you take action k, right? And then, with probability P00k, you leave state 0, and you may, well, in principle, you may come back to state 0 under action k, and then we multiply this with what? The relative value of the state into which we have just moved in under the old policy, which is R1 in this case. Then we just do this for every possible state to which we can move in one step from state 0. So we can go from, in principle, from 0 to 0, even if the probability equals 0. I don't care at the moment. Or we may go from 0 to 1 under policy k with this probability. We multiply this quantity with relative value of state 1 under policy, old policy R1. And from 0, we may move to state 2 under policy k with this probability. We multiply this probability with the relative value of state 2 under policy, old policy R1. Okay? What else do I have? And finally, we may move from state 0 to 3 under action k with this probability. We multiply this with the relative value, okay, right, like this. Actually, perhaps we should we write all these values? Okay, I'll do that in a moment. Minus the relative value of state 0, which is V0 under old policy R1. Right? We have just calculated these numbers. So these things do not really depend on neither the state nor the action that I take. So let us just write them here then, so that I can copy them for others quickly. So this was what? Relative value of state 0 under old policy. What do you read over there? Minus 4,077. How about this? Relative value of state 1. 15. Okay. And relative value of state 2 is 2,154. This is always 0, and in fact we can just erase that then altogether. But we don't forget that we subtract the relative value of state 0, right? In this case it is minus, again, 4,077. Right? We have this for state 0. For state 1, what do we have? Immediate expected cost in state 1, incurred in state 1 when we take action k. From state 1, right? We can go to state 0 with probability, when we take action k with this probability, we multiply with the relative value of state 0, which is minus 4,077. This is now with probability 0, 1 of k, we move from 0 to 1 in one step, which is irrelevant, right? We should be looking at the probability that in one step we go from 1 to 1 under action k. We multiply this with the relative value of state 1 under old policy, which is always this number. Here, starting initially in state 1, I go to state 2 under action k with this probability. We multiply this with relative value of state 2, which is 2,154, and minus relative value of state 1 under old policy, which is, I guess this, right, minus 2,615. Okay, I have that. For state 2, immediate expected cost under action K is given by C2K. For each K I have different numbers, so we'll come back to that. Plus, from state 2, we may go to state 0 under action K with this probability. And you multiply this with relative value of state 0, which is, as before, minus 4077 under old policy, plus, we were in state 2. In one step, we may go from 2 to state 1 under action K with this one-step probability. And the relative value of state 1 is again minus 2615 plus, and with probability P2 to K, right? In one step, we may go from 2 state, or come back to state 2 under action K with this probability times the relative value of state 2. We copy that, 2154 minus relative value of state 2, which we can copy again from this column if you wish. It is 2154. And finally, for the last state, the immediate expected cost, C3K, right, plus, from state 3, we may go to state 0 under action K with this probability. We multiply this with relative value of state 0, which is minus 4077, plus, from state 3, we can go to state 1 under action K with this probability. We again multiply this with the initial relative value of state 1, which is again minus 2615, and plus, right, we can go from 3 to state 2 under action K with this probability. This is multiplied with relative value of state 2, which is 2154 under old policy, minus relative value of state 3 under old policy, which is 0. Very well. Yeah, that's it, right? So we have all these things. What do I know? What do I do now? So we already wrote here what we should do, right? For each of these states, right? I have to find what R2 is supposed to prescribe. How do I find it? That's the K, right? So these are all true in principle for every possible K between 1 and 3. There are 3 possible decisions we can choose from. And I will, for each state, for each line, I have to find K which is going to minimize each line on its own. But then there is a good news, right? What is the good news? In state 0, how many possibilities are there? Well, only action 1 can be taken. None of the others, other actions are relevant. Actually, we don't have anything to minimize over here. It is just 1. So R2 has R2 1, R2 0. I'm sorry, should be 1. Okay. Similarly, in state 3, overhauling doesn't help. We cannot just let the machine stay dead all the time, so we cannot take action 1 or 2. And the only action, so it is still the second policy, the only action that we can take in this state 3 is 3 that we have to replace. So we have more than one alternatives only in stage 1 and 2, right? For each possible case, in state 1, what are the feasible case? Feasible values of K, what I mean, right? We may just choose not to do anything, or overhauling doesn't help, or we may just replace. In state 2, what are possible actions we may take? We may choose to do nothing, or overhaul, or replace. And there are all three possibilities are available to us in state 2. So let's first look at state 1. Okay? So for each of these cases, what do I need to know? Immediate costs and one-step transition probabilities under those actions. Let's make a table of that. Now we are looking at state 1, the possibilities in state 1, right? So I guess, okay, decision K is important. I have to know immediate K, so state 1 means now I equals 1. So immediate expected cost, I need to know that. What else do I need to know? One-step transitions. We know that these are all zeros, but should I put them over there? Why don't I do that? 1, 0K, 1, 1K, 1, 2K, and 1, 3K. Right? And then at the end, I will plug all these numbers into this equation for each possible case, 1 and 3, and I will calculate what? The value of policy improvement quantity. Improvement quantity. After that, what should I do? I will find whichever gives the minimum. I'll take that action and say that new policy, R2, has to choose in state 1 the action whichever gives the minimum quantity here. Okay? Alright, what are these? You do nothing in state 1, therefore you have to live with the cost of defective items, which is $1,000 per week. You do nothing, no, you replace, right? If you replace, then the cost is what? The cost of the new machine plus the cost of the production that you lose over the 1 week period when you have to replace this thing, it is 6. If you do nothing, what are the transition probabilities? You cannot get anything as good as new from something imperfect. It may come back with probability 3/4, or it can worsen. The state of the chain can worsen with equal probabilities, 1/8 each. Right? And here, if you replace, you know that you will get a new machine with probability 1. Right? Now, we take the first line, replace all unknowns in this, not this one, in this equation. You get a number, which I am going to copy from my notes. Where is that? It is 1,923 for if you choose to do nothing. Okay, if you choose to replace, this becomes 4,538. And the minimum is what? This. Therefore, in state 1, the new policy has to choose action what? Do nothing. Okay? Do nothing. Okay? Any questions by now? It's just bookkeeping, right? If you have a computer, life is easier, but then this is a good exercise. At least we should do at least once so that we understand what is going on. It would be nice actually to ask you, maybe you should write one program just to do that. Huh? Would you like to do that? I remember Osman Oz asked us to code primal dual algorithm just in order for us to understand the algorithm very well. See, I still remember. Okay, I'll think about whether this is a good idea or not. Okay, for state 2, right? That's the other state where there are more than one alternatives that we can choose from. So therefore, we have to decide which one is the best. So we can actually construct a similar table. So decision K as before. Right now C2K. When we are in state 2 rather than 1, in state 2, when we choose action K, what are the immediate costs? We have to look at all of them. And one-step transition probabilities under each of these actions. Going from state 2 to 0, or from 2 to 1, or from 2 to 2, and from 2 to 3, right? And then we should also check again the value of policy improvement quantity. Okay? Possible actions are 1, 2, or 3. Okay? And the costs. If you do nothing, now 2 is a more serious state, you pay more for the defective items, and we know that it is $3,000. It's still here. Okay? If machine is in state, no, it is always in state 2, right? If you choose to overhaul the machine, you pay 4,000. 2 for overhauling, 2 for the lost production during the 1 week period. And then transition, no, before that, this is always 6, we know that. Right? Let us look at the transition probabilities. If you do nothing, this is 0. You cannot get any better machine if you do nothing, right? And with probability 1/2, it stays the same. And with probability 1/2, the machine gets worse, right? And then what happens here, if you take decision 2 instead, then with probability 1, the machine is going to be in a better position, namely in state 1, and 0 otherwise. Right? If you take action 3, then you are replacing machine with a brand new, therefore, with probability 1, you move from 2 to 0. And what do? We take the second, the equation corresponding to the second state. For k equals 1, we plug all these numbers, you get something which is 1,923 for this one. For if you take action 2, namely if you decide to overhaul the machine, you get minus 769. If you decide to replace, you get minus 231. And your decision is what? 2. Because that gives the smallest value of policy improvement quantity. So our 2 of 2 equals 2, right? Okay. All right. So we are, what happened? Now we are done with step 2 as well, right? Now next step is what? We should check if this new policy is optimal or not. We can, in the meantime, check whether this is better than the old policy or not. Long run expected average cost. Where is that? It is not here yet. So I don't know what it is. We have to just run actually another iteration to find it. But just first we have to check whether there is really a need for going for another iteration or not. And the check is, optimality check is easy, right? We ask to ourselves if this R2 policy and R1 policy are identical or not. Are they? Are they the same? Huh? Do they prescribe the same actions in all of the states? Are the actions they prescribe in all the states are the same? I should ask like that, right? No, right? The answer is no, because here, if you put the other in the same sequence, it is 1, 1, 2, 3. That's how the policy looks like. New policy. The old policy was 1, 1, 1, 3. They are different, right? Therefore, we have to do another iteration, right? So we have to do another iteration. Okay, where can I do that? Am I going to use any one of these values? Not really. So we can then, can I switch the boards here? Did you take notes of everything on that? Okay, now we look at we have to do at least one more iteration, right? For this one, right? We can first summarize, right? We start now with, maybe I should say, we are now starting this iteration with R2. And what is this? We can look at the decisions we make under this policy in each of these states, and more importantly, the costs, immediate cost, right? The cost CI under policy R2, right? Immediate cost. States are 0, 1, 2, 3. Decisions we make 1, 1, 2, 3. Costs, immediate costs we incur are 0, 1, and 4 this time because we are overhauling, not 3 but 4. And in the last state, when we replace, we pay $6. Okay. Okay. All right. And what do we do? Starting with this, the first step is to determine the values of all these variables associated with this new policy, right? Value determination step. And we again write what? These equations. The relative value we assign to last state under this new policy R2 is again equals 0. In state 0, what do I have? Long run expected average cost under policy R2 this time equals, you can look at the one-step transition probabilities for this one. It is going to be different than the ones under old policy R1, right? Not in a drastic way. The change is not drastic, but we still have to take into account, right? So we have 7/8 here, 1/16 for each of these arcs. Right? From 1, we don't do anything. We choose to do nothing, right? Whenever we are in this state. So with probability 3/4, we stay here. With probability 1/8, we move to state 2, and with probability 1/8, we may move to worse state. This is not nice. I need more space. Okay, so it is like, okay, with probability 1/2, we may move to state 1, or with probability, no, 1/8, sorry. We may move to worse state 3. And now in state 2, unlike policy R1, under R2, we overhaul, that means with probability 1, we may move to state, we are going to move to state 1 from 2, and in state 3 we always replace the machine, therefore with probability 1 we are going to move from 3 to 0, sorry. So that's the one-step transition matrix I have to use as I write these equations, right? So let's do that. In state 0, immediate expected cost equals 0 plus, right? We have one-step transition probability going from 0 to state, state what? So I can just look at from state 0, I can go to 1 with probability 7/8, and I multiply this with relative value of state 1 under policy R2. Am I right? Right? Okay, plus with probability 1/16, we may go to state 2, therefore we multiply this with the relative value of state 2 under policy R2, and we don't really have to write this because the relative value equals 0, minus the relative value of this state, which is V0 of R2, right? And for state 1, long run expected average cost under policy R2 equals expected immediate cost under 1, state 1, which is 1, plus from 1, in one step you can come back to itself. With this probability you multiply it with the relative value of the same state under R2, new policy, plus, and then from 1 you may go to state 2 with probability 1/8. We multiply this with the relative value of state into which we move, and state 3 doesn't count, even though we go there because we multiply with 0 again, minus the relative value of state 1. under new policy R2. For state 2, this equation is going to be shorter because what? Under policy R2, right? First of all, we always pay expected immediate cost 4 plus with probability 1. Now we will always go from state 2 to 1. This is then 1 times the relative value associated with the state into which we go, V1 of R1 minus, okay, let me write minus relative value of state 2. V1 of R2, that's a good point. Okay, that's great. In state 3, what's going on in state 3? We start as always the long run expected average cost per time unit under policy R2 and the expected immediate cost when you are in this state and you take action or you follow policy R2 plus with probability 1 now you move to state 0, so you have the relative value of state 0 under policy R2 times 1 minus relative value of state 3, which is 0. We have all these equality system of linear equations for 4 unknowns, right? We can solve them and we find the simultaneous solution to be is this. Long run expected average cost per time unit for this new policy is 1,667, and we have relative value of state 0 under policy R2 equal minus 4,333, and the relative value of state 1 under policy R2 minus 3,000, and relative value of state 2 under policy R2 equals minus only 667, and the relative value of the last state, as always, equals 0. Right? We have this, and in the meantime, let's just check whether this was really a good policy, better than the first one. Where are my numbers? Right? The long run expected average cost per time unit for R1, the initial one, 1,923. This is around 300 less. Right? So, okay. It's always good to check these things. You can then identify a mistake in case you make a mistake, which is quite probable in my case. Okay. So what happens now? And in this case, we have to just go on with step 2, right? And find a policy which is hopefully better than this one. Hopefully better for the sake of the entire system, right? You may just, okay. May want actually this just stop here so that we don't have to go through this pain for another iteration, but we'll see what happens. The policy improvement step. So here now we are looking for what? Well, maybe I shouldn't say that. Right? We already know how to construct it. Okay, find a new policy R3, right, which consists of what? Actions to be assigned to each of these states. Such that, okay, maybe I should say the which assigns to each state I an action K, minimizing the following policy improvement quantities. Okay. All right. And what are they? So as before, we know in state 0 and 3, we don't have any choice but just choose either action 1 or 3, right? So our 3 of 0 must be 1, and our 3 of 3, right? If the system machine is good as new, we have no choice but do nothing. If the machine is inoperable, we have to replace it. So this must be 3 as well. So we only have to worry about, again, state, the actions that we have to take in state 1 and in state 2. Okay? For each one of them, right, the quantities that the policy improvement quantities becomes like this. Expected immediate cost, right? P with probability P1 0k, we move from state 1 to 0, and we multiply this with relative value of state 0, which is this, right? Minus 4,333, plus we move from 2 to 1 under policy, under action K with this probability. We multiply this with relative value of state 1, which is state 1, relative value of state 1 under old policy, which is now R2, right? Which is minus 3,000, okay? Plus, right? Okay. Maybe I should just write. Okay, I am going to write here. With probability, with the following probability, we move from 1 to 1 under policy K. Okay, we have to move actually from 2 to 2, right? No, what am I doing? We started with 1, right? So this should have been 1, 1. This is going to be 1, 2. And then we multiply this with the relative value of state 2 under old policy, which is minus 667. And plus, right, with probability 1, 3, we will gonna move to state 3, but its relative value equals 0, so we don't really worry about that. And minus the relative value of this state under old policy R2, which is this. Huh? Why? No, it is state 1, right? We wrote for all those states in previous, we know that we already know the answer for state 0, so I quickly move to state 1. So the relative value of state 1, what is relevant in this case, it is minus 3,000, right? I don't have any space left, so I just write there. So I would like to put everything here. For state 2, so you again start with immediate expected reward. You incur when you are in state 2, and if you take action K, with probability 20k, you move from 0 to from state 2 to 0 under action K. Now the relative value of state 0 is as before, minus 4,333, plus we move from 2 to 1 under action K with this probability. In one step, we multiply this with the relative value of state 1, which is again, right, minus 3,000, plus we move from 2 to state 2, or we come back to state 2 in this case, right? Under action K, if we take action K with this probability, we multiply this with the relative value of state 2 under old policy R2, which is minus 667 as before, and state 3 doesn't count, minus the relative value of this state, which is, what is that? Minus 667. Minus itself, which is the negative number. So let's just be careful about that. So what do? You again see all of them depend on K, but we already actually identified all this information in the previous step, so we don't have to do that all the time, right? Whenever you are in state 1, if you take action K, there was this table. I shouldn't have actually written on this board. I knew that. Anyway, okay, I made that mistake. So we already know very well what this algorithm is. Let me just quickly summarize those numbers and then finish this lecture. Okay. All right. Here are the relevant numbers. So when you take decision K in state I, or in state, well, in this case I need 2 columns for each. In either state 1 or state 2, then the policy improvement quantity becomes like this. Okay. So you may take action 1, 2, or 3. Okay, action 2 is irrelevant in state 1, so we don't have a number over there. All right. For in state 1, okay, namely you evaluate this expression 4k, 1 and 3. You get numbers 1667 if k equals 1, if k equals 3, if you replace the machine, decide to replace the machine, this becomes 4667. For state 2, all 3 actions are feasible. You may take one of them, and you take the second equation, right? You put numbers for probabilities and immediate expected costs, and you find policy improvement quantity to be 3,333 for k equals 1 if you decide not to do anything. If you decide to overhaul the system, this cost, or well, this quantity becomes 1,667. And if you decide to replace the machine, then the cost, well, this quantity becomes 2,334. Right? Okay. What are R3 of 1 and R3 of 2? What are they? 1 and 2, because this is minimum for state 1, and this gives the minimum quantity, policy improvement quantity for state 2, right? So, what do we conclude? R3 is 1. In state 0 it was 1. We don't do anything. In state 1 we decide not to do anything. In state 2 we are going to overhaul, and in state 3 we have to replace. Right? So now we have to do this optimality check or optimality test, right? But what do we see? R3 is in fact the same as R2. Right? We found actually this before, so they are the same. So the conclusion is what? Well, we stop. The policy improvement algorithm stops, right? Policy improvement algorithm stops with an optimal, I write too fast. Optimal stationary deterministic policy R2 in this case, in fact, 1, 1, 2, 3. And what do we do? What is the meaning of this? Do nothing. In state 0 and 1, overhaul the machine if it is in state 2, and we should replace the machine in state 3, right? Which was the same policy we found, I guess, when we used linear programming and enumeration. Okay, I guess we should stop here, right? I cannot hold you anymore here. All right, so what is the situation? So I was unable to start with Poisson process. That's bad news. Therefore, we definitely have the first class before the exam. All right?